Hi, everybody. This is a lecture on section 5.5, which is on alternating series. So an alternating series sum n equals 0 or n equals 1 to infinity, or wherever you might be starting, an is said to be alternating if the even terms are positive and the odd terms, so let me write it this way. If all a 2k plus 1 are positive and all a 2k are negative, or all a 2k plus 1 are negative and all a 2k are positive. All right. In other words, the terms flip-flop, positive, negative, either the odd terms are the positive ones or the even terms are the positive ones. Okay. Therefore, every alternating series sum n equals 0 to infinity or 1 to infinity is of the form sum n equals 0 to infinity minus 1 to the n bn, or sum n equals 0 to infinity minus 1 to the n minus 1 bn, where the bn is positive for all n. Well, not positive, but non-negative. Okay, so, well, no, it would have to be positive. Is positive for all n, right? So this one has the even terms positive. This one has the odd terms positive. So negative 1 to the n minus 1 or negative 1 to the n plus 1, either one would do fine. All right, just something to start off to make the even term negative. All right. Telling when an alternating series converges is a lot easier than for series in which all the terms are positive. So this is the alternating series test. So if the sequence is positive and decreasing, right? So if an is a sequence that's positive and decreasing, then sum minus 1 to the n an, the alternating series, minus 1 to the an, or minus 1 to the n times an, or sum n equals different color, or sum n equals 0 to infinity minus 1 to the n minus 1 an, right? So there's always two choices for how you alternate it. Either the first term is positive or the first term is negative. So if an is positive and decreasing, then the alternating series converges if and only if AN converges to 0. That's a striking thing, right? Before, we had the following. If the series converges, then the terms go to 0. If the series converges, then the terms must go to 0. But just because the terms do go to 0, it does not mean the series converges. That changes with alternating series. With alternating series, it goes both ways. The series converges if and only if the terms go to 0. Pretty cool. And the way in which it converges is very interesting, I think. So let's take a look. But let's talk about what we just said before we get into the proof of that. So observations. So with series in general, especially series with positive terms, okay, AN converging to 0 does not imply sum n equals 0 to infinity AN converges. Right, so for examples, right, the sum 1 over n equals 1 to infinity, 1 over n to the p diverges for p's between 0 and 1. Right, those p series, that's the standard example. But now when you alternate it, it must converge. However, with alternating series, sum n equals 1 to infinity, 1 over minus 1 to the n over n to the p always converges because converges for any p bigger than 0, because 1 over n to the p converges to 0 itself. So all those p series, when you alternate them, they must converge. And they converge to pretty cool things, actually. A lot of sort of unexpected things pop out of that. All right, let's take a look at the proof for the alternating series test. Okay, we know that, so we proved already, that sum minus 1 to the n, AN, converges implies that AN goes to 0. Now, assume that AN goes to 0, and we will prove that, let's make this start at 0. The sum n equals 0 to infinity AN converges, or not that one, minus 1 to the n AN converges. Okay? Well, let's look at the partial sums, okay? The partial sum S0 is equal to A0. The partial sum S1 is A0 minus A1. The partial sum S2 is A0 minus A1 plus A2. S3, A0 minus A1 plus A2 minus A3. S4, right, A0 minus A1 plus A2 minus A3 plus A4, so on and so forth, right? And keep in mind that AN is positive and decreasing. Therefore, the partial sums on the number line look as follows. Alright, so here is A1, say. So that's S, no, not S1, A1. That's S0, right, which is equal to A0. And then you're subtracting to get S1. Let's put it over here. Whoops. So here's partial sum S1, which is equal to A0 minus A1. And the distance between these two, right, is A1. Right? The difference between these two guys is A1. Alright, let's take the next partial sum. So the next partial sum, S2, is A0 minus A1 plus A2. Now where is that? Well, it must be here. Is A0, and then this is S2, A0 minus A1 plus A2. Now, why is it in between S1 and S0? Why is it in between? Well, because the distance from here to here is A2, which is less than A1, because, right, those terms are decreasing. Okay, what comes next? Write this a little differently. A2, where A2 is less than A1. So since A2 is less than A1, that partial sum S2 can't go all the way over here. It has to be here somewhere. Next. Third partial sum. S3, so S1 is equal to A0 minus A1. And then S3, well, it's got to be here. S3 is equal to A0 minus A1 plus A2 minus A3. And the distance from S2 to S3 is A3. Right, where A3 is less than A2. Again, the A's are decreasing, right? So S3, you're subtracting off A3, so it goes over here, but not clear over here to the left of S1. It has to be to the right of S1. So it's to the left of S2 and to the right of S1, in between S3. So it just keeps going like this. Etc., etc. You just keep going like that. Oops, with the partial sums. Alright, there's S0, S1, S2, S3, S4, S5, S6, where this distance, put another one in there, S7, where this distance between the two is the next term, or the last term, A7. And because AN converges to 0, that distance is getting tinier and tinier and going to 0. So there must be some limit L in between. So thus L is the limit as n goes to infinity, or as n goes to infinity of the partial sums Sn. I guess I should use a different letter. As k goes to infinity, Sk, but that's the sum, n equals 0 to infinity, minus 1 to the n, An. So there has to be a limit, because this distance is just closing up to 0. There's got to be something inside there. All right, great. So let's check it out. Let's do some examples. Sum n equals 0 to infinity, minus 1 to the n, over n factorial 5 to the n. Right? N factorial and 5 to the n are increasing functions. So 1 over n factorial 5 to the n is decreasing. Right, so that's a decreasing function. Is decreasing, and certainly 5 to the n and n factorial are both going to infinity. We get that 1 over n factorial 5 to the n converges to 0. Thus, the sum n equals 0 to infinity minus 1 to the n factorial 5 to the n converges. So that's great. I mean, that's very interesting. But what is even more interesting about that alternating series property, the fact that those partial sums are just jumping back and forth like that, is that it becomes easy to estimate an alternating series. Like, I mean, here's some number, some series, and we know it converges. Can we estimate it now? Now, this one actually we could figure out what it is exactly. It's actually e to the minus 1/5. That right there, and we'll see why that's so in chapter 6. Right? Why that's actually e to the minus 1/5. But let's talk about how do you estimate an alternating series. Right, so given a convergent alternating series, sum n equals 0 to infinity minus 1 to the n, an, or minus 1 to the n minus 1, either one. Given a convergent alternating series, the nth remainder Sn, which is equal to the sum, or the kth, I guess. The kth remainder, Sk, which is the sum, n equals k plus 1 to infinity minus 1 to the n, an, satisfies that Sk is less than or equal to ak plus 1. Right? So, oops. Kth remainder Rk, and S is for partial sum. Rk is less than or equal to ak minus 1, ak plus 1. So there's a difference of 1 in the indices. Right? This is the k plus first term. This is the kth remainder. Why is that so? Right, so on the number line, right, here is partial sum Sk. Here is partial sum Sk plus 1. Right, partial sum kth partial sum. And that's the k plus first partial sum. All right, and these guys are flip-flopping back and forth. And in between them is the limit. But the distance between these two, right, is the term ak plus 1. ak plus 1. But the remainders is just the kth remainder, Rk, is right here. So the distance from here to here is ak plus 1, but the kth remainder is just this, Rk. Right, the kth remainder is the difference between the partial sum and the full sum. And we see that, because these partial sums are flip-flopping back and forth like that, that the remainder is always less than the next term. Pretty cool. So let's go back to that problem here that we did before. And let's estimate using that alternating series error estimate. So estimate the sum using the alternating series error bound. Estimate with, let's say, estimate with 5 decimal places of accuracy. Estimate, now let's say, estimate with error less than 10 to the minus 6. Compare with the actual sum, which is e to the minus 1/5. Okay, so we're going to compare to that. Okay, well, the kth remainder is less than or equal to the k plus first term. So let's do it this way. Instead of using that the kth remainder is less than or equal to the k plus first term. Let's do like this. The k minus first remainder is less than or equal to a k, just to make the arithmetic a little easier. And make that less than 10 to the minus 6. Okay? So what we need to pay attention to now is this part. That's what we need to pay attention to. So we want this to be less than 10 to the minus 6. We don't know what this is. We don't know what that is exactly. But what we do know is that it's less than this. So since the remainder is less than this, and we know what that is, it's just this right here. 1 over n factorial 5 to the n. Without the alternating business. 1 over n factorial 5 to the n. You just make that less than 10 to the minus 6. Okay? So this is 1 over, now of course we've switched letters, k factorial 5 to the k. Was it e to the, yeah. K factorial 5 to the k less than 10 to the minus 6. So now, in lieu of being able to solve for k, I mean, we can't solve for k here because I mean, you know, it contains factorials. We don't know how to deal with factorials, how to solve equations. Like, you know, n factorial equal to 7. I mean, that doesn't even make sense. You know, you can't really solve it. So in lieu of being able to solve, just guess. For k, just make a guess. So let's try what? So this is 1/1,000,000th. So we'll try k equal to 5. K equal to 5. Try k equal to 5. Alright, so for k equal to 5, 1 over 5 factorial 5 to the 5 is equal to, well, what's it equal to? So 5 to the 5th is that, times 5 factorial is 120, is this. So that's 1 over 375,000, which is not less than 10 to the minus 6. Right, which is not less than 1 over 1,000,000. Alright, so we got to go up one more. K equal to 6. So 1 over 6 factorial 5 to the 6. I believe that's going to do it. So 5 to the 6th is that, times 6 factorial. It's this, 11,250,000. Right, that is less than 1 over. Right, so we have that for k equal to 6, this inequality is satisfied. So which partial sum should we use? The k minus first remainder is less than the kth term. So we don't have to use the 6th partial sum, use the 5th partial sum. Right? So the 5th partial sum will give us an estimate with error less than 10 to the minus 6. Not the 5th partial. The 5th partial, sorry, not the 6th partial sum. The 6th partial sum will as well, because the error just keeps getting smaller and smaller. But you can go down by 1. So I mean, you can do the 6th partial sum if you want, but the 5th will suffice. Alright, so the sum n equals 0 to infinity minus 1 to the n over n factorial 5 to the n is approximately equal to the sum n equals 0 to 5 minus 1 to the n over n factorial 5 to the n, which is equal to, so n equal to 0, by the way, 0 factorial is 1. Okay, it's not 0. 0 factorial is 1. That's by convention. Right? So for 0, this is just 1. Minus at 1, it's a fifth. Plus at 2, this is 2 times 5, that's 1 over 50. At n equal to 3, this is, so 5 to the third is 125, and 3 factorial is 6, so that's 750. And then for 4, five to the fourth times 4 factorial, 15,000. Minus, and then at 5, we've already calculated it, it's 1 over 375,000. Alright, so this is equal to, make that smaller so we can see where we're at. Alright. So we've got 1 minus 1/5 plus 1/50th minus 1/750th plus 1/15,000 minus 1 over 375,000 gives us 0.818730. Oops. 0.818730. 1, 2, 3, 4, 5, 6, and then a bunch of 6's after that. Okay. So there's the estimate that we had. Now, the exact answer is e to the minus 1/5, and let's see what that is. So I think it's this. So 0.2 negative exponential. Oh, that's not it. How does this work? So there's e. 0.5 negative. So 0.606 will happen. So that is e to the minus 1/5. 1/5 is 0.2. 1 minus a fifth plus a 50th minus 750 plus 15,000 minus 1 over 375,000. E to the minus, oh, I put the wrong exponent. So it's e the 0.2 minus, there it is, 818,73075. 73075. Right, so we got 1, 2, 3, 4, 5 decimal places of accuracy. Actually, we got 6 decimal places of accuracy. 1, 2, 3, 4, 5, 6. Alright, so we get 6 we got Okay. So that's a second type of series that we now know how to estimate. I mean, we're doing series that we actually know the answer to, just so we can do some comparison. But we will have problems in which we won't know how to actually sum up the series. Okay, so we'll do some more of these in class, but for the third exam, I'm going to ask you to estimate an alternating series using this technique and to estimate a positive term, the sum of a positive term series using the integrals. So that integral bound on the error. So two different types of estimations, one for error alternating series and one for the positive term series. One using integration and one just using that the k minus first partial remain the k minus first remainder is less than or equal to the kth term. Okay, one cannot be done. So one type of problem is for alternating series, one type of problem is for series with positive terms, and you can't use them interchangeably. Okay, one does not work for the other, so they're completely separate techniques. There's no series in which you could use both. All right. Final topic here is just some what's the term? Just some terminology. So absolute convergence, conditional convergence, so absolute convergence, I guess, versus conditional convergence. So definition. So given a convergent series, sum n equals 0 to infinity an. So I'm not saying it's alternating or not, or positive term or negative terms or whatever. I'm not saying anything about that. Given a convergent series like that, we say, so this converges. So we say that the sum an converges absolutely when it really, really converges. I mean, when sum n equals 0 to infinity of the positive terms converges as well. Okay, so that's what absolute convergence means. And then we say converges conditionally. I guess I didn't write that nicely. When this sum series for the positive terms diverges. Right? So you got a series. Some of the terms are positive, some of the terms are negative. If all the terms are positive, then absolute convergence just means convergence. But if some of the terms are positive, some of the terms are negative, okay, we say that the series converges absolutely when the series of positive terms also converges. And then the series converges conditionally when the series of positive terms diverge. So, for example, and this is just vocabulary. So, the sum n equals 1 to infinity minus 1 to the n over n squared converges absolutely because the absolute value of the terms is just 1 over n squared, converges. The sum n equals 1 to infinity minus 1 to the n over n itself, that converges conditionally. Right? 1 over n goes to 0. 1 over n goes to 0, and that's an alternating series, and it's decreasing. And that's an alternating series. So the alternating series test, it says that that converges. This converges conditionally because the series of positive terms, just 1 over n, diverges. And the sum n equals 1 to infinity, something like this. Minus 1 to the n, 3n plus 1 over 5n plus 2. That one diverges because 3n plus 1 over 5n plus 2, well, that converges to 3/5, which isn't 0. Okay? So there's three sorts of situations with alternating series. You can converge absolutely, like this one. Converge conditionally, like this one. And that's conditional convergence. It does converge. The alternating harmonic series does converge because 1 over n goes to 0. Right? That's good enough for alternating series, but for non-alternating series, it isn't. Okay? So this one converges conditionally because the series of positive terms diverges. This one converges absolutely because the series of positive terms also converges. And this one just diverges. Okay? Because the terms don't go to 0. All right? So that's the lecture on this section.